started, I guess. My name is Kevin Coakley. I work for the San Diego Supercomputer Center, and I work as a programmer there, helping out with cloud and other initiatives. So my talk here is on reproducibility in AI and what computing professionals should know when supporting researchers. So I will get started then. Okay, much has been said about a reproducibility crisis in science, and artificial reproducibility and artificial intelligence has also been included in that as an example from this science article from 2018. Okay, so what is reproducibility? There's a lot of confusion about what reproducibility exactly means. A lot of people confuse repeatability, replicability, and reproducibility. And I apologize that those terms are so close together. It's hard for me even to pronounce the differences. But the differences between those three can differ between scientific disciplines. And also the definitions of those three terms also it changes over time as the literature evolves on reproducibility. So in analytical chemistry, they have a concept of a within run, which is when an experiment is done by the same staff in the same lab with the same solution, same equipment, same procedure at the same time. And a between run, which is the experiment that is done by different staff, different lab, different equipment, but the same procedure at a different time. And so in analytical chemistry, repeatability is the within run and reproducibility is the between run. And the authors note that it is expected there will be larger random errors with the reproducibility of the between runs when it's done by different people, different labs, just because there is, just because it's very difficult to reproduce something exactly somewhere else. In June 2016, the ACM released what their definitions for these terms. So for repeatability, they said it was the same team, same experiment setup, which is the same as the repeatability in analytic chemistry. For reproducibility, they said it was a different team, a different experiment setup, which there was no I did not find a definition in analytical chemistry for that. And what they called replicability, different team, same experiment setup, that was what reproducibility was in analytical chemistry. And these definitions were inspired by the international vocabulary of metrology. Well, in August of 2020, the ACM revised their definitions of what these terms were, and they switched reproducibility and replicability to match the terms that analytical chemistry. This was based off of discussions with the National Information Standards Institute. And so even people like ACM aren't able to it's difficult to define these terms, which makes the crisis in reproducibility even more difficult if people aren't even sure what they're talking about, what the terms mean. And so perhaps a better way to think about reproducibility is to think about it in terms of the scientific method. So in the scientific method, you have the world, we form beliefs about the world. Based on those beliefs, we we create a scientific theory, we create a hypothesis to test that theory, and an experiment to test our hypothesis. We run the experiment. Once the experiments are done, we get the outcomes, we analyze the outcomes, and we interpret the analysis. And then based on that interpretation, we update our beliefs of the world. But for reproducibility, according in the terms of the scientific method, it really only happens at the last three parts: the outcome, the analysis, and the interpretation. So we could think of reproducibility then in terms of the scientific method. And so something could be outcomes reproducible, meaning like you rerun the original experiment and you get the same exact results. And so you're able to reproduce the outcomes. Or you could say something was analysis reproducible, where somebody reproduces the experiment in a different lab, and they may not exactly get the exact same outcomes, but when they perform analysis on those outcomes, it may be the same. For example, if you take the average or something, the averages might be the same even though the outcome was different. Or it could be the experiment could be interpretation reproducible, where neither the outcomes nor the analysis were reproduced or replicated exactly, but the interpretations of the analysis were able to be confirmed based on somebody rerunning the experiment in their own labs. And so in order to achieve reproducibility, information needs to be given about the experiment. And so there are 4 degrees of information that can be provided to reproduce an experiment. The lowest degree is just a textual description of how the experiment was produced. And so then the next level would be providing the code. So you have the textual description and the code, but then you don't have other things like the data or the lab configuration, or how they, the computer setup for the experiment. Then the third degree of information for reproducibility is providing the data. So you have the textual description and the data, but somebody trying to reproduce the experiment will have to come up with a code to run the experiment and also the experiment setup. And the fourth level is the experiment. So this is where everything is shared. So you have the text description, the code, the data, and how the computer lab was set up. And so here's a graphical representation of that. So any good experiment should be able to be reproduced, even no matter what degree is provided, but the 4th degree should be the most likely for an experiment to be reproduced. However, lab bias still makes, even if you have all the text, all the code, all the data, all, a complete documentation of how the computer lab was set up, it still could be difficult to reproduce the experiment. And the reason why is there's lab bias. So these 2 machines are mass spectrometers. And so it's known in chemistry that 2 different mass spectrometers will give a different output on the same sample. And that even though that these outputs are different, the conclusions of what is in the sample is usually the same though. And so I don't know if people really think about computers in the same way as they think of other lab equipment, but it's been shown that running the same models on different computer systems will produce different results. And these impacts of these differences between the computer labs on these models has been understudied on how it affects the conclusions. And so there's these sources of variability that are in computer systems that cause all of these differences. The sources are processing units, operating systems, ancillary software, software versions, and compiler options. So processing units, CPUs. So floating point arithmetic is not as easy as it sounds. Depending on how you round numbers or where you round numbers, it'll give you a different result when you're processing algorithms. Also threading. So given that A plus B equals E and C plus D equals F, it cannot be ensured that A plus B plus C plus D will equal E plus F. And so if you run a machine learning training model on a multi-threaded system, depending on how many threads, you could get different results, because if you run, say, on 2 threads, you'll get the result of E plus F. If you run it on 4 threads, you'll get A plus B plus C plus D. And GPUs are another source of variability. It's arguably a greater source of variability than CPUs. You could have differences between different GPU models, and even within the same GPU model, manufacturers are free to deviate from reference standards provided by NVIDIA and AMD. And then there's some factors that cannot be controlled, for instance, the number of threads. So the reason why GPUs are so popular is because they have so many threads and they're so good at a floating point arithmetic that there's so many threads that with CPUs, you could generally pin it to a certain number of threads, but for GPUs, that is often not possible. And so here's an example of how the GPUs and CPUs can affect the output of a machine learning algorithm. So this is an algorithm for exploring the effectiveness of a convolutional neural network for answer selection and end-to-end questions and answerings using the TREC-AQ and WikiQA data sets. And so when it was run, you can see the differences when it was run on between the GeForce, the Tesla versus the Intel. The differences aren't statistically significant, but it does show that there is something going on where the different processing units where everything else is the same is causing there to be some variation, some bias. And so now, with the popularity of machine learning, the cloud providers especially are providing other processing units beyond just CPUs and GPUs. FPGAs and ASICs, or tensor processing units, as Google calls them, are becoming increasingly popular. Unlike CPUs, the hardware is proprietary, the specs aren't fully open. There are people who are making clones of these TPUs, and these clones may achieve API compatibility, but I haven't seen any studies on whether or not they're fully reproducible, the outcomes. And then even reproducibility between generations has not been studied. But I believe Google is now on their 4th generation of TPUs, or the 4th generation of TPUs are coming out. So experiments ran on previous generations may produce different, or likely to produce different results as they often would on GPUs. And so ancillary software is another source of variability. Ancillary software is just most people don't write their own software from scratch. They often include other libraries and those dependencies, and those dependencies may also have other dependencies in libraries, and so it could be a complicated web to even know what all the ancillary software is. But here is the same experiment as I mentioned before, where the output of when the effect of changing the math library for linear algebra on the when the framework from Intel's math kernel library to the open DLAS, you could see that that there is a difference between just everything else being the same hardware, that it would produce a different result. And in fact, in case of the math kernel library from Intel, because it's Intel specific, you even get a different output based on if you're using Intel or AMD CPUs. And software versions are another big source of variability. Again, when the previous experiment was run using the PyTorch framework with version 0.1, the results were almost identical, but switching to version 0.2, there was actually a statistically significant difference in the results. And that, when people upgrade software, they include different ancillary software. Maybe those software versions change of the ancillary software, or maybe it's just the developers of the software figure out that they have a more efficient algorithm, and they refactor their code, and that code will often lead to variations. And so it's important to note that. And compiler options, again, every CPU, every new generation has new instruction sets. Most of these instruction sets are for optimizing floating point arithmetic, and the amount of speed and efficiency that these new instructions add often make it difficult for, if you're trying to make something that runs fast and efficiently, you have to include them in order to gain those efficiencies. And the differences come from different approximations to math functions. Intermediate results are often calculated differently with these special instructions. Very small numbers are sometimes treated as zero, and it may include new and special instructions that just simplify other math problems. And so the last source of variability that I go over is operating systems. And operating systems are a combination of ancillary software versions, and compiler options. I don't think anybody would really expect a model trained with PyTorch on Windows to necessarily give the same result as on Mac OS or Linux. Even the differences between Linux and Ubuntu can be great. Different kernel that is running, different versions of the different libraries. So it's a combination of all of those. And so containers have been put forth as a solution for variability of the operating system, but I haven't seen any papers on the effects of how using containers can contain at least this source of variability. And also, you may have to give up different speed optimizations in order to achieve compatibility across different hardware environments for containers. And also, just machine learning is an inherently random process. If you have a neural network, when you initialize the different layers, random weights are assigned to these different layers. When data sets are often divided into mini batches in order to avoid a local minima, so those mini batches can be different every time it's run. If you have too much data, oftentimes the framework will choose a random sample of the data. If you have too little data, sometimes the data will be used for training, sometimes the same data will be used for tests, and so that will also cause some randomness in it, which will cause variations in the results. And then also, just in order to prevent overfitting, a lot of times the frameworks will include hidden layers, which also have random weights and initialization variables. And so from all of this, to sort of like get an idea of how this bias is working, or how this bias is changing the reproducibility, borrowing from analytical chemistry again, they have this equation where they could sort of calculate the variance that is being caused in an experiment by taking the standard deviation of when somebody reproduced it in their own lab versus the standard deviation of the repeatability of an experiment in their own lab. And so in order to do that, you can sort of calculate this variance for this specific experiment for the bias, and then you could sort of use that to, when you're doing your analysis, to sort of factor that in while you're making your interpretations. So, like I said, even with laboratory bias and a low degree of documentation, experiments should still be able to achieve reproducibility. So this is an example from the CG Sense. They did a reproducibility challenge where they're trying to recreate the results of a MRI reconstruction algorithm from Pressman. In his published article, it was just the algorithm was published, no code was produced. And so they had 11 teams from around the world try and recreate the implementation. They were not given any sort of restrictions on what hardware, software, what programming language they could use or anything like that. And so this was the results. As you can see in the bottom, that they all had basically got a pretty close approximation to the exact same result. And when they reviewed it, they concluded that all 11 teams were able to successfully reproduce the paper from Prusman. And so it shows that, that even though there are biases and documentation and other issues, that people are able to reproduce these studies. And so, I want to stress that, only the interpretation according to the scientific method, only the interpretation needs to be identical, not the results. And I think it's important that, when doing machine learning and other experiments on a computer, that, to keep in mind that there are biases in the hardware and in the software, and that these need to be factored in and thought of when coming to drawing conclusions. And perhaps if you rerun the experiment in a different lab and you look at the standard deviation of the differences, maybe there needs to be a contextual adjustment when you're publishing a paper, giving an explanation of why this might happen. Or perhaps it needs to be, the experiment needs to be conducted in more environments in order to be fully trusted, because you have to keep in mind that these things these biases are real, and you wouldn't want to have something in your conclusions because of a bias and not because of the science. And so I think that was my last slide. So yeah, if you have any comments or suggestions or questions, there's my email address. You can contact me, and I think we still have a few minutes if anyone has any questions or comments.